Good afternoon, everyone, and welcome to today's Safer Sim webinar. Today's presentation we'll discuss a current research effort from the University of Central Florida that's focused on developing transportation planning simulation framework to generate exposure information for crash prediction models. So I'm happy to welcome the presenter for today, Professor Naveen Eluru from the University of Central Florida.
Thanks for the introduction. So in today's presentation, I'll talk about how we developed a transportation planning approach to improve non-motorized safety. For this purpose, we simulated non-motorized exposure information. Before I start the talk, I would like to acknowledge my team members who worked on this project. Sham Sunahara Yasmin is a postdoctoral associate working on this project. She was the lead of the research effort along with my team members, my PhD students Tanmay Baumik and Moshir Rahman. This is the brief outline of my presentation. I'll present the motivation for our study, explain the research plan, then discuss the empirical context, the framework that we used for the analysis, and then I'll start presenting some results, some policy analysis, and then I'll conclude my presentation. The motivation for undertaking this study is very clear. Non-motorized modes of transportation, both walking and bicycling, are sustainable green transport alternatives. Further, they also provide individuals with physical activity benefits. Given the increasing attention devoted to obesity and its ensuing health problems, it is beneficial to have individuals doing more walking and bicycling so that they can get the additional advantage of being physically active and getting some exercise. Given these obvious benefits, transportation decision makers across various countries, not just in the US, but across various countries, are proactively encouraging adoption of these active forms of transportation. For example, one policy initiative that has been regularly being considered is the installation of bicycle sharing systems across multiple urban regions in the world. I think at last count, there are about 1,000 cities that are either considering or have already installed bicycle sharing systems. A good example in the US would be the New York City bike system, which is functioning regularly with a lot of activity. So there is a lot of investments going into bicycling and walking, but there is a significant impediment to this, which is the associated crash risk. A number of pedestrians and bicyclists are involved in crashes, and this reduces the likelihood that we can grow the population of bicyclists and walking. So while there is different policy initiatives to improve these non-motorized modes, there is also a limit drawback among individuals because they're worried about their safety. The safety challenge is even higher in Florida. Florida, is apart from the summer months, usually, except when we don't have hurricanes, we usually have good weather, and they should be conducive to walking and biking. But unfortunately, the average pedestrian fatalities and bicyclist fatalities are some of the highest in the country. So the rates are about 4 times to 6 times higher between uh, pedestrians in Florida versus rest of the nation. So clearly there are infrastructural issues. There is no there is reason for us to investigate this so as to address this challenge. Uh, there are different levels at which this analysis can be undertaken to improve safety for pedestrians and bicyclists. There could be analysis at a geometric design level, improving intersection safety, improving segment level safety, treatments on these facilities. Or we can also look at this from a very high level picture, which is the planning level, where we are trying to understand where are the incentives going, how are that benefiting in improving pedestrian and bicyclist activity, and how is that activity being translated in terms of crash risk. So this current research effort is at the planning level. We're focusing on the, the macro level analysis from the beginning of policy investments. Uh, Typically, the policy analysis, the planning analysis would focus on developing crash frequency models and crash severity models. So in terms of crash frequency models, we are interested in modeling the number of crashes, and we are trying to understand what are the factors that influence these number of crashes so that we can develop effective countermeasures. So if you're looking at it at a macro level or a zonal level, the crashes are related to number of intersections in the zone, what is the proportion of 3-lane roads, 2-lane roads, 1-lane highways, length of median. These are the variables that are used usually in developing crash frequency models. And the empirical, the mathematical model structure used typically is the negative binomial, which is the most commonly used crash frequency model. In terms of severity, the emphasis here is on the not only on the number of crashes, but we are interested in understanding the impact of the crash. So is it a no injury crash or is it a fatal crash? So that is what is examined in crash severity models. So in this, the typical model structures used take the form of either ordered logit models. Again, there have been studies where multinomial logit models and other extensions of these models have been used, but typically the approach used is an ordered logit. Now, when crash frequency models and severity models are developed, ideally, if you're looking at a macro level or a intersection level crash frequency model, you would like to know what is the number of pedestrians or number of bicyclists on that facility. So this is what we call exposure. Having exposure, we can directly relate the risk of the individuals to exposure in addition to geometry and other factors. However, obtaining non-motorized exposure information is quite challenging. So there is a huge drawback within the transportation safety area for non-motorized safety. Now, in addition to addressing the lack of this information for safety models, there is another big picture issue. If we do not know or do not have a good prediction model for that for non-motorized demand, we don't know what is happening with investments. So if you're building a bicycle facility, we would like to develop a model that captures the sensitivity of pedestrian or bicycle demand to these facilities. So we built a nice path for bicyclists where again it shared path for both bicyclists and pedestrians. If you can develop a model that can capture its impact on the demand generation part, it would be useful as a policy tool for analysts to say, okay, we are spending in so many dollars, that is allowing us to increase our walking and biking activity by so much. So even from that perspective, non-motorized exposure is very important. So there are two reasons why we are looking at exposure. One is to understand how demand varies, and other is use exposure as an important exogenous variable in predicting crash frequency and severity. Uh, Again, there are some approaches. For example, if you look at any high resolution modeling frameworks such as activity based models or trip based models, these are planning level frameworks that provide activities or trips and associated mode share. Now, the challenge with using these is, first of all, they're computationally quite expensive. Building them from ground up is very hard to do. And more importantly, their focus is mainly on vehicular travel. So the resolution of non-motorized travel in these systems is usually not very high because their emphasis and focus is on predicting vehicular volumes, traffic volumes on roads, public transit usage, and so on. So their emphasis is a little different from what non-motorized safety models would like. So if typical literature in non-motorized safety can be represented in this figure, you have crash frequency analysis and crash severity analysis. Because of the lack of true non-motorized exposure data, it's a huge drawback in the quality of the outputs that are being generated in these systems. So it is in this context that we are undertaking the study. Our objective is to address the link between non-motorized demand and safety. So if we have a good demand model, and then if that can be used to generate exposure, and that exposure feeds into the safety model, you have a seamless evaluation of how demand is increasing or reducing, how that is having an impact on improving or making safety worse. So for this purpose, we have three broad steps in our research effort. The first part focuses on generating non-motorized demand. And in this part, we explicitly recognize that pedestrian demand and bicyclist demand are different. So we have separate modules for pedestrian demand and bicycle demand at a zonal level. Then, given the demand generation, we use those to create our exposure matrices. These are exposure matrices going from different zones to different zones. This is like analogous to the origin destination matrix in the transportation for vehicular flows. Finally, given the information in the first two steps, we develop aggregate level non-motorist crash frequency and severity proportion models. The figure here represents what we are trying to do. So we want to start with the non-motorist exposure. We have non-motorist demand, their trip duration and length, and that exposure feeds into the non-motorist safety. That's where you get the crash frequency and crash severity models. And within the middle figure, we have the different characteristics that we'll consider. The demand and safety are a function of roadway and traffic attributes, land use characteristics, built environment, and socio-demographic characteristics. So we account for this in a unified, seamless framework. So the three broad steps are again described here. So we want to develop an integrated framework of non-motorized demand and safety, and in that context, we'll develop aggregate level. I'm saying aggregate level here because the exposure models are developed at a zone level, so at a traffic analysis zone level. Then these aggregate matrices that are developed from the exposure model are used to create our matrices for safety evaluation. These matrices feed into the non-motorist crash frequency and severity proportion models. Again, the crash frequency and severity models are also developed at a macro level. So the analysis dependent variable would be number of crashes occurring at a zone level. So in the remainder of the presentation, we'll talk of these three separate modules as different steps. In terms of non-motorist demand, as I mentioned, we recognize that pedestrians and bicyclists have distinct behavior. So we allow for a separate model for pedestrian generation, pedestrian attraction, and bicycle generation and bicycle attraction. Here we'll use information on pedestrian origin demand and destination demand and so on to generate these models. Then the predicted demand matrices from the previous step are compiled to generate the measures for safety evaluation. These are the matrices that will be used in the in the third step. The third step models, we develop crash models also separately for pedestrians and bicyclists. So there are crash models for pedestrian safety, crash models for bicycle safety, and then we also have severity models both for pedestrians and bicyclists. The study area for our research is the Central Florida regional area. So this is the region that is covered in our analysis. It has 4,747 traffic analysis zones. We have 9 counties. I don't know if many of you are familiar with the Florida plan system. Florida has 7 districts. The Orlando region is part of District 5. So the study region encapsulates District 5 and also small parts of District 1 and District 4. And the study analysis is based on the base year of 2010 because of the data availability. In terms of data preparation, the exposure model in our analysis is built using the 2009 National Household Travel Survey. Of the What we did to compile the data was we looked at the individuals residing within this area as part of the household survey, and we obtained 2,750 households, about 5,000 individuals, and within this we had a reasonable number of walk and bike trips. So these were used in our analysis. So this component of the data was used to generate the exposure demand generation models. For safety, uh, UCF has extensive access to the DOT data, and we've been working on this for a long time. So we used the crash analysis reporting system and signal 4 analytics datasets. Within this data, there are about 1,474 pedestrian crashes and 1,000 bicycle crashes in our dataset. In terms of other independent variables, we spent a lot of time compiling and building GIS data sets. So we have a lot of socio-demographic attributes, roadway and traffic attributes, built environment characteristics, land use characteristics, and exposure measures generated. So these are all used in the different models. Now let's look at the details of the first step where we are developing exposure models. So uh, the figure here shows you, the top two figures show you the demand for pedestrians uh, for origin and destination. Similarly, bicyclists for origin and destination. I don't know if how many of you are familiar with the region. So the highly red areas are usually around CBDs, so Orlando downtown or Sanford downtown, Kissimmee. So these are areas where you would expect a lot of walking because there is significant high-rise buildings and activities going on. In terms of bicycling, the activity sphere is much smaller. As you would expect, it is much low. The usage of bicycling is a little lower on the lower end. It's only 2% relative to 8 to 9% for pedestrians. So you'll see less highlighted area for in terms of zones for bicycling activity. These are the summary tables for the different models that we are trying to do. In terms of demand, if you look at it, the average demand is about, for all the zones, is about 265 trips for pedestrians and 35 trips for bicyclists. Uh, and we, we, we need to recognize that to generate these numbers from the sample, we used the NHTS provided weights. So the corresponding population weights were used to get the number of bicycling and walking trips at the zonal level for the entire population, because we cannot just sum up the number of trips for the pedestrians that are available in the data, because they don't represent all bicycling trips in the region. So we use the survey weights to accumulate the number that would represent the population numbers for each zone. We also have the crash frequency details here for the pedestrian crash model and the bicycle crash model. Now, one challenge with developing the demand matrices was that we found that a large number of zones had zero pedestrian and bicycle activity. So, for example, for pedestrians, it is about 84% and 96% of the zones have zero bicycle trip modes. Again, this is not very surprising given the mode share for pedestrians and bicyclists in the dataset. And in typically from our experience in Florida, usually you'll find a lot of pedestrian bicycle activity only around the urban centers, such as, for example, UCF campus is one of those activity centers, or the shopping complexes. But whereas in the suburban area, the number of these trips are much lower. So what we decided to do was we decided to use a model that can accommodate for the zeros in the dataset. So instead of using a simple negative binomial, we went ahead and used a hurdle negative binomial model, because it explicitly recognizes that only when the propensity crosses a particular hurdle, there is going to be trips associated with the zone. For other zones, there are no trips. The mathematical formulation for the hurdle model is provided here. So the equation here is the same as the negative binomial model, but you also have a yes or no equation that captures whether there is going to be any activity or not, and if so, what would be the number of trips for that person. And again, everywhere we use these models, we recognize the person weight, and we use that weight in developing estimates that are accurate. I'm not presenting all the results for the models. They could be reviewed from the report, or if you are interested, you can write an email to me and I can provide those numbers. I'll just provide the results that are the findings that are interesting. For example, uh, again, because it's a hurdle model, there are two components: the probabilistic component and the count component. Probabilistic component contributes to whether there will be trips or not, and the count identifies the number of trips. So land use makes urban area, number of households, increases the probability that there will be walk trips, as you would expect. Similarly, the number of trips is affected by the population, proportion of seniors, proportion of arterial loads, length of sidewalk, as you would expect. And if you have a lot of recreational area, residential area, office, it increases the number of walk trips. In terms of pedestrian, in terms of decreasing it, if you have high average zonal speed, so this is the average computed as the average of all the speed limits in the zone, and higher speeds indicate more vehicular activity and less conducive to pedestrian activity. Similarly, very high AADTs also discourage people from walking and biking, and the presence of industrial area or presence of large proportions of 3 or more lane roads also reduces activity. The results are very similar for the attraction and two. So the pedestrian generator models are estimated using origin information, and the attractor models are generated using destination information. We conducted similar models. Again, the hurdle models are even more relevant for bicycle zones, because bicycle models, because we have only 4% of the zones which have non-zero activity. Again, we use similar variables in both the systems, and the results are quite close across these systems. So for the models were developed, and to test the validity of these models, we conducted a validation exercise. What we did was we predicted the values of total zones with zero trip count, total number of zonal trips, and average zonal trips from the data and from our models. So from the results, you can see that the predicted values are really close to the observed values, showing that the models that we developed are doing a very good job. So for example, if you look at the bicycle generator model, the total zones with zero trip count are about 4,574. In our case, it is about 4,573. In terms of the average, we are under predicting it by 0.12, which is a very small error in this case. So from this system, we were able to develop models for estimating demand, so both origins and destinations for both pedestrians and bicyclists. Using that, we created the exposure matrices in the second step. So for this purpose, given the origin, we could model the destination. To do this, we developed a destination choice model. In this case, what we are doing is we are examining the impact of zonal attributes on the influence of destination location. So for this purpose, we have a pedestrian destination model and a bicyclist destination model. Again, you recognize that the distance people would walk versus distance people would bike would be substantially different. You will expect people biking to go for longer distances. So it is useful to keep these separate model as separate. We used a random utility approach. The idea that individuals choose the alternative location that gives them the highest utility. Uh, so in this context, it's important to recognize that unlike vehicular trips, the destination choice is much more narrower in the case of pedestrians and bicyclists, because if you're driving, so this activity space can be the entire urban region. So theoretically, all 4,747 zones are potential candidate locations for you to go to. On the other hand, if you're walking or biking, the number of zones that are accessible reduce substantially. Particularly for walking, it's much lower. For biking, it's even lower. So what we did was we created a choice set observing behavior in the data set. We found that very few people walked more than 2 miles in the data set. Similarly, very few people biked more than 6 miles. So what we did was we created choice sets customized to each zone based on whether they were accessible within 2 miles for pedestrians or whether they were accessible within 6 miles. So a particular zone could have 5 alternatives, another zone if it could have 12 or 15 alternatives, depending on the size of the zone and depending on how close the other neighboring zones are. And this is important because you don't want to consider alternatives that are not going to be viable for individuals. And here we only develop the destination model considering zonal level attributes, because we are trying to develop a macro level model. We don't have the ability to use individual level variables because we won't have this information when we do the prediction. This is the mathematical framework for the multinomial logit model. You have a simple utility expression uh, where you have the numerator, which is the utility for the choice alternative of interest, and the summation across all alternatives. And the individual chooses the alternative that gives them the highest utility. Even here, we considered the weight as we mentioned before. In terms of destination choice, the likelihood that a particular zone is chosen increases if it has high population density, proportion of 65 plus individuals. So we are observing that individuals who are 65 and higher are likely to be engaged in a lot of more walking than compared to the rest of the population. Traffic signals increases the likelihood that a choice is chosen, because the presence of traffic signal implies the possibility for a pedestrian phase in the signal, which makes it easier for people to cross those roads, unlike when you do not have any traffic signal. Similarly, if you have a lot of financial activity, say restaurant and transit hubs, urban or residential and institutional areas, institutions would be universities and so on, they are likely to increase the chance that a particular location is chosen as a destination. Again, the variables that offer negative characteristics are also quite intuitive. If you have very high AADT, truck AADT, those reduce these the chance that the destination is chosen. In terms of the bicycling behavior also, they're slightly similar, but sometimes we notice interesting results here. If you look at population density, that's a variable that is a positive sign for the pedestrians, but it has a negative sign for bicyclists. Similarly, number of restaurants. It's possible that bicyclists use their activity not to go to restaurants because they'll probably sweat, and it's not a they cannot do this in formal attire and so on. So but walking on the other hand is not as physically intensive, so it is possible that the behavior for different variables across these two models can be substantially different. Again, this supports the reasoning behind why we developed two separate models for our analysis. Now the next part of the research was to develop trip O-D matrices. So given we have the O-D origin demand using predictions from the non-motorized model, we also developed both predictions for origin and destination, and then we used the summation of these two to create our exposure matrices. So what we did was we have the trip origin demand and the trip destination demand, and we added those two to get the total trip demand. This gives you an indication of number of individuals walking in those zones. So here we are presenting you a brief summary of the results. We are focused on just showing you the results for all the counties. So these are the various county names, and these are the number of TSEs within each of them. So the total number of TSEs are the 4747 that we used in our model analysis. So these trip demands the table is created at a county level just for presentation. We create this matrix at a zonal level so that this can be used as an input variable in our safety models. The third step in this analysis is the development of the safety model. So where we are developing two, two kinds of safety models. One is the crash frequency and the other is crash severity. So this is the representation of both pedestrian and bicycle crashes in the data in the for year 2020. You'll see the darker the shade of red, the more severe is it, higher are the number of crashes. So they could be the yellow represents zero crashes. So we'll see that there's a lot more pedestrian crashes than bicycle crashes. Again, this is expected because we have more pedestrian activity compared to bicycle activity. These are the different characteristics. So even here we have about 3,798 zones with no crashes and 949 with crashes, and similarly 4,000 zones without crashes and 700 crashes for bicycles. And in addition to the number of crashes, we are also interested in identifying the number of crashes by severity. Because we're developing a model at the macro level, uh, we could either model the different crash counts by severity, or we could model the proportions. So in this approach, we use a recently developed methodology that we developed in our group to do severity analysis. So what we do here is we do a frequency model, get the total number of crashes in the zone, and then we develop a proportion model that gives us the proportion of each type of crash. So let's say if there are 10 crashes in a particular zone, we would like to know how many of those are no injury, how many of those are minor injury, and how many of those are non-incapacitating, incapacitating, and fatal. This information is obtained from the proportion. So if it is 20% are fatalities, it will give you out of 10 crashes, 20% would give you 2 crashes. So instead of developing 5 models where you develop separate models for each of these crash numbers, we use a joint system where we have a crash frequency model and a crash proportion model that can simultaneously provide the same information. So with increasing numbers of dependent variables, if you use a multivariate model, the number of dimensions can increase. In our case, irrespective of the number of crash severity alternatives, we have the same 2 equations required for our model analysis. For the crash frequency model, we just used a negative binomial. Again, the formulation is very similar to what is typically used in research. And then we use this to compute the log likelihood and estimate the model. In terms of crash frequency, again, we developed separate models for pedestrians and bicyclists. We'll see that population density, uh, traffic signal density, proportion of arterial roads, length of sidewalk, all of these variables increase the number of crash counts. Having fewer, having higher number of older individuals and increasing pedestrian demand actually reduces crash counts. So again, this is an indication that high pedestrian demand makes drivers aware of pedestrian activity in these zones, and drivers are prepared to stop for pedestrians, and thus the advantage of safety in numbers comes into the picture here. On the other hand, for bicyclists, unfortunately the safety in numbers does not come into the picture. We actually notice that bicycle demand increases risk. So bicycle demand in the region is still at a level where more bicyclists result in more crashes, whereas pedestrian demand is at a stage where increasing demand actually helps reducing crash risk. So this is an interesting relationship that we find in our analysis, both for pedestrians and bicyclists in terms of frequency. Again, whenever we develop models, we develop validation measures. So here we are predicting the different validation measures. We developed the mean prediction bias, mean absolute deviation. The formulas are available there, and you'll see that the numbers clearly show we're doing a very good job in terms of representing the observed data. So for example, in this graphs here, we are plotting number of zones with 0 crashes and number of zones with 0 crashes predicted. The green bars represent the prediction, blue bars represent the actual observed values, and you'll see that our model does a very good job in aligning to that. Same thing for bicycles also. In terms of the crashes, the mean pedestrian crashes is 0.31 and the corresponding predicted number is 0.33, so showing that the error is reasonably small. So far we have talked about crash frequency models. Now we'll move into the crash severity component. As I mentioned, the crash severity here is modeled as a proportion variable. So given uh, n number of crashes, some of them are fatal, some of them are incapacitating, and so on, we create a new variable, the fraction of crashes, by doing this. So we divide the fatal count with total crash count. So if there are 2 crashes out of 10 total, 2 fatal crashes out of a total of 10 crashes, the dependent variable for the fraction would be 0.2, and we'll use these variables as our dependent variable and develop what is known as an ordered fractional split model. So because we have fractions of crashes at each zone level, so we do not model the total number of crashes for each injury category. We actually develop the ordered probit fractional split model to study crash severity by levels. Again, here is the different proportions that we observed in the data. Property damage is about 0.11, fatality is about 0.09, but we observe a large weightage for non-incapacitating and incapacitating injuries. So this is quite different from driver injury severity. If you are a car driver and you're injured, a largest share of injury severity is in the property damage or minor injuries. But for pedestrians and bicyclists, you observe that more than 50% of the weightage for injury lies in the more severe categories. Same here also, we'll have a larger share, severity proportion in these two alternatives. Again, this highlights how crash risk, the occurrence of a crash, is substantially detrimental to non-motorists relative to other vehicle occupants or drivers. So these are the different severity outcomes that we generated. So the larger is the red share, the higher is the risk in those regions. So this is the no injury, this is possible injury, incapacitating, and this is the fatal injury crash. Again, this is just to illustrate how the risk varies. So you'll notice that zones which have high fatal crashes, fatal injury crashes, crash risk do not necessarily have higher injury crash risk also. So this shows that spatially there are differences across what kinds of crashes are likely in different zones. This is again a similar figure for bicycle crashes. You'll see, fortunately, there is very small number of fatal crashes, but you'll see a very large share of non-incapacitating and incapacitating injuries for bicyclists also. Uh, I won't provide too many details on the methodology. Again, I'll be happy to discuss this offline through email or any question if you have any questions. The idea is very similar to the ordered logit model, but here what we have is you have a variable which is no longer discrete, because in an ordered logit model the choice variables are 0, 1, 2, 3 and so on. Here we have fractions. So the typical maximum likelihood approach will not work. So what we need to do is we need to resort to what is called a quasi likelihood function. The propensity is similar to what an ordered logit response model will have, but here we create a fractional split model based on a quasi likelihood based approach. Here what we do is we define a function that adds up to 1 across all alternatives, which is what we need, and then optimize that function. The formulation we used takes the form of an ordered probit structure because of the error term assumption that we make, and this would be how the log likelihood function would look like. Again, given the time, I'm not spending too much time on this, but I'll be happy to discuss this offline. In terms of the crash proportion models, so there's only one crash proportion equation for both for pedestrians and then one more for bicyclists. In terms of the proportions, we find that as VMT increases, we find the proportion of higher severity categories increases. Presence of urban area, increased urban pedestrian trip demand reduces the proportion of severe crashes. So again, here also for pedestrians, we notice the advantage of safety in numbers. So more pedestrians, most pedestrian demand, even if crashes occur, their severity are likely to be on the lower end because people are expecting pedestrians in those zones. Bicycles, on the other hand, benefit from presence of school signals, park and recreational centers, residential areas, and a flashing beacon. Population density uh, is beneficial to them. Sorry, these are the variables that increase the risk. Availability of bike lane substantially reduces risk. Bicycle trip demand also reduces risk. So again, in terms of crash frequency, bicycles safety in numbers does not apply, but in terms of crash severity, more bicyclists actually benefits bicyclists in improving their safety and reducing the severity risk. So again, the main emphasis of why we developed all of this is to undertake a detailed policy scenario analysis. Our objective was to see if we impose some scenarios on the urban region, what will happen to bicycle demand, pedestrian demand, and corresponding safety measures. So what we did was we identified different variable impacts and we computed percentage changes. So we did it for all zones. We looked at it for pedestrians and bicyclists separately, and we also identified multiple CBDs in the Central Florida region. So uh, let me go over some of the scenarios. So as you can see, we tried a lot of scenarios. I'll focus on a couple of them. So in the first, I'll talk about scenario one. What we did here was we reduced traffic volumes around CBDs. So we created a buffer around the CBDs and we said we are implementing a road diet kind of scenario where only half the number of vehicles that are currently allowed are allowed onto the roads. So what this does is reduces VMT. So when we did this, we observed that using the demand models for walk and bike, because VMT reduced and the number of lanes have reduced, so we have increased walk and bike activity. So this is the change in the zonal demand, and we looked at change in crash counts. So you'll see that number of crashes for walking reduce, but number of crashes for bicycling increase. Again, this directly relates to the relationship of demand, and safety. So because for walking, the safety and numbers is applying in our data set, that in our region, it continues. So increasing walking activity actually reduces risk. So more people walking reduces the crashes. On the other hand, for biking, it's not so clear. Here we have uh, more people biking increases risk. So this is what happens for the entire study region. But we also uh, focused on zones where these changes were made. So if we looked at that, we'll notice that both for walking and biking, crashes actually reduce. So here we have the total number of demand increases substantially in these regions, and there's a clear-cut reduction in both walking activity and biking activity. And the same applies for the severity. We observe the same reduction for walking and biking for the fatality group. Again, we can show these numbers for all injury severities. We're only focusing on fatal crashes. Then we also looked at another scenario, for example, here where we said all zones have uh, sidewalks. So in our analysis, we found that some zones did not have sidewalks. So we created a variable where we increased sidewalk activity for sidewalk for everybody, and looked at increasing the sidewalk to a particular measure. In this case, we observed that bicycling demand increases, whereas walk demand reduces, but walk safety is still better, but bicycle safety worsens. So same, but we find that severity wise, it's still on the better side. So what we are observing in across these scenarios, again, we discussed each of these scenarios in detail in the report. What we observe here is that pedestrians in general benefit from increasing demand. Bicyclists, the picture is not so clear cut. In some cases, it can improve their safety. In some cases, it can be detrimental to them. Okay, so this is the findings that we have from our policy scenarios. Uh, I'll quickly conclude my presentation. So what we did in our research is we developed an integrated non-motorized demand and crash prediction framework. We identify and incorporate different exposure for non-motorists. We propose the three-step framework where we have demand model, exposure matrix generation, and the safety models. And all of this has been conducted separately for pedestrians and bicyclists. So we estimated a lot of models, 8 different models, four for pedestrians and four for safety. And again, these provide useful insights on mobility and safety changes associated with a host of hypothetical scenarios that we developed. Again, to be sure, we recognize that there are several limitations. Ideally, developing exposure models is not very easy. Here, we were able to do it because we had access to NHTS data with those survey weights. Again, it might not be readily transferable if you want to do a micro level model. So, for example, if you're interested in intersection level exposure measures, it might be challenging to do that with these weights. Uh, in the future research, we want to look at predicting safety and demand for a future year and see. So because we used our base year from 2010, it might be an interesting exercise to look at into the future and see how things look for the Orlando region and the Central Florida region, and that would be of interest to us, and we'll probably work on that as an extension for this research. With that, I complete my presentation. I think I finished 2 minutes early probably. Uh, and I'm happy to take any questions at this point.
Yep, thank you for the presentation, Naveen. Um, for any participants that would like to ask a question, there is a chat box at the bottom right of your window. So we have a couple people typing right now. Naveen, I can read the questions out loud for you if you need me to.
Okay. Okay.
Okay, so the first question, can you comment on how you may think the sample size for the bike data is affecting your results?
So because we created this information at a zonal level, uh, if the again it ties into the quality of the NHTS survey. So we had about the 2% or 3% of the trips out of the 22,000 trips that we had. 2% of them were bike trips, which gives us a reasonable number. Obviously, we would like to have more uh, bike trips. But that's a challenge that we face in collecting data of this kind. In terms of how it would affect our results, I think for zones where there is a lot of bicycle activity, I don't think it'll affect a lot because the survey would have covered those zones. But the zones where there is occasional activity, there we would have gotten zeros from our survey information because the chances that they are compiled are wrong. So we would probably be overestimating the number of zeros in the data set potentially. So that could be the challenge that we might have to look into if we have to address the sample size issue for bike data. Again, if that answers your question, let me know.
Okay. Um, so Don Marshall here at Iowa told you thank you for the great presentation. What connections do you see between these models and human in the loop research? Is that close or does it require more work to make a connection?
Again, I am assuming when you say human in the loop is we provide them information based on the safety and how they can use that information. Uh, I would say somewhere in the middle. We are not very close, but at the same time, we are not very far. I think uh, this information the analysis that we did could be used to make those connections. But I think we are doing a planning level model. So to get to individual level trips would require us to develop a connecting system where we use the aggregate level information that we are generating from here. Okay. Yeah, it would require us to disaggregate. So I see what you're saying. So it would require us to convert these zonal level measures to local specific origin destination coordinates. I think once we do that, I think we can go ahead and do the simulation in terms of the actual origins and destinations, because right now we are doing this at a slightly aggregate level than what is required for developing a simulation system that you were thinking about. I think it's a very good question. So that would be the potential next step on, given we have so many trips being made from this origin to this destination, where will they start? Where will which is the facilities, which are the roadway facilities they'll be using for pedestrians and bicyclists, so that we can get intersection level exposure measures. So how many people are walking on this intersection of the roadway? Right now, our models are slightly at a higher, uh, I would say less accurate resolution. So that would be something we'll have to make a connection to. I hope that answers your question. One of my co-authors wants to add something, so I'm waiting for her to type that. Yeah, so what you're saying is the framework that we developed here would actually serve as the base models. Yes, this would be the higher level base scenario for the human in the loop modeling perspective. Yeah, I agree with that. Okay. So one more the point that Shams my postdoc is making is the models that we developed as base scenario can serve as a base scenario for the human in the loop modeling perspective because as is apparent data on pedestrians and bicycle activities are very limited. So if we can use the models that we develop and generate this information, we could use them as a starting point to conduct the analysis. I think that's the main use or benefit from our work relative to the uh, conversion it converting it into human in the loop research.
Yeah, I agree. That's a great connection, as Don just mentioned there in the comments. Yeah, well, great discussion, everyone. I guess if there are any follow-up questions, you can see Naveen left that URL on the screen. You can find him online to get more information if you need to contact him directly. Um, we will be putting this webinar up online on our Safer Sim YouTube channel within the next couple days, so you can look for that. Feel free to pass that along to any of your colleagues who might be interested. So I want to thank you all for coming and attending this presentation today, and thank you, Naveen, for giving the presentation. Tomorrow we'll be having our virtual symposium for Safer Sim, so if you are registered for that, we will see you here tomorrow morning.
Yeah.
All right, thanks.
Thanks everyone for your patience and yeah, thanks for attending.